Okay, thank you all for joining this week. Um, Dr. Basil Tikoff is a quantitative field geologist who's joining us this week, who, with his group, applies geological field mapping, kinetic modeling, microstructural analysis, paleomagnetism and AMS, and gravity surveys to problems often focus on shear zones. Some of the core areas of research include tectonics of the Western United States, granite emplacement and magmatic arc processes, strike-slip tectonism, and deformation of the lithospheric mantle. Basil received his physics BA from Oberlin College in Ohio with a minor in geology, and from there went on to study under Christian Teyssier for his PhD at the University of Minnesota, where he worked on shear and strain modeling, fabric analysis, and continental tectonics. He next was a postdoctoral fellow at the same institution. After the postdoc, Bessel became assistant professor at Rice University, and a few years later moved to the University of Wisconsin, where he is today and has established a strong research group for decades studying dynamic questions in structural geology. Today, he will tell us about the Paleoarchean Dome-and-Keel structures of the East Pilbara Craton. Please take it away, Basil.
All right, thank you. So Ian, I assume you can see the presentation at this point?
Yes, looks great.
Excellent. So thank you for the invitation. I'm going to tell you about some work we've been doing for about the last decade in the Pilbara Craton. I'm going to concentrate on a couple, basically one area. So the Mount Edgar, Corunna Downs, Warrawoona Syncline area and see what we get. I have worked with a lot of collaborators on this project, and I was very lucky to have a very accomplished graduate student named Nick Roberts who worked on this. He's already given a talk in this series. So, and he has done more detail in his talk about the anisotropy of magnetic susceptibility and then the dome features. So, if you're more interested in that, that would be a way, it might be worth looking up his talk. So Nick, Jeff Bord, and Ross Salerno all did a project together, and that's mostly the geochronology and magnetic fabrics. On the right-hand side are Paul Kelso and Ann Everest, and we're mostly working on the geophysics. And what's really nice about this project is trying to put it all together. So we've been working very much as a coordinated group to sort of try and use all these approaches at once to see what we can get. So the talk overview, I'm going to give you first a little bit about why we're doing it. I'm then going to talk about the domes and then the geochronology, which is on both the domes and the keels. And then I'm going to move over to the keels to talk a little bit about the microstructures we see there, and then the gravity analysis. I am not going to oversell this talk. After working here for a decade, I still don't quite understand if plate tectonics was active at this time or not. So I'm going to tell you basically what we found and what we're thinking about, but it's very much a work in progress. So I like to do this. For the people with short attention spans, here's basically the punchline right now. We've been thinking about this idea of convective overturn, which I'll go into, the idea that the dense parts basically get pushed down in the early Earth, and and then the domes rise as a result of that. And there are aspects of that that work, and there's aspects of it that don't work. Basically, the features from the domes, the internal fabrics, and so forth say this looks like a reasonably good model. The garnet geochronology indicates that the deformation is happening with that magmatism, which is what you'd expect with that model. But then there's problems with that model, which is that there's some very odd shear sense indicators on the sides of Mount Edgar, and there's no indication that there's a deep basaltic root below what has been proposed as a zone of sinking. So I'll go through that during this talk. This group probably needs no introduction to the general topic of whether plate tectonics were active at this time. we can all agree they're active in the Phanerozoic, and then after that, we don't really know. There's a lot of disagreements. What's interesting is if you look at the age of Pilbara rocks on a plot of global zircon, uranium lead distribution versus age, and the age of the Pilbara is about 3.2 to 3.5. It's proposed to be a time of different kinds of tectonics, but maybe sort of a stagnant lid. And it's relatively undisturbed by later events. So it's really quite a good place to look at it. Um, just a couple different models for different places and people who've inferred different times. So some of the early work in for the Eoarchean in West Greenland suggests that there's plate tectonics is going on. In the North Superior Province, a little later suggested that it's not the plate tectonics isn't going on, and rather it's mantle plume and crustal delamination. And then the model I'm going to focus most on with this talk is the idea of partial convective overturn, with this idea that you get a greenstone on top of a protocrust, and then that greenstone sinks into the lower crust, middle and lower crust, and then drives the upward flow of the dome. And so that in part comes out of the Pilbara Craton. This is just a more detailed slide of that, just showing the process of the greenstones coming down, starting Raleigh-Taylor instability, and allowing a periodic upward flow of domes. And so it's a density um, inversion. So it's a buoyancy caused problems. And that if this is true, there must be positive gravity anomalies underneath the greenstone keels, and they must go deep. That's, again, the suggestion from the modeling. So, of all the places you could work to sort of figure out these problems, here's some places with just some of the people who've been working there highlighted. And we went to the East Pilbara Craton because mostly what you can see is it's Archean rocks, but they're not reworked Archean rocks, and they're relatively well exposed. So what's nice is you can even see the area from a Landsat image. So we're looking at that white box. And then as you go in, you can see the granites from space. So Mount Edgar here, Corunna Downs there, and then here's the Warrawoona. I will talk a little bit about the Shaw Pluton, which is the next one to the west from the Corunna Downs. So if you go there, you know that the granites are basically the flat areas. The greenstones are the upland areas. The contacts are pretty sharp. The exposures, as you pick between the spinifex bushes, it's pretty good there. You can see a relatively good outcrops in this area. The timing for this East Pilbara Craton is about 3.5 to 3.2 billion years. It is overlain by this gray material. This is the Fortescue Formation to the north, the Hammersley to the south. And then the West Pilbara Craton was affected by younger orogeny, so we're not going to talk about that area. So again, we're in the 3.5, 3.2 range here. With some younger magmatism, we get some 2.8 billion year old magmatism affecting the East Pilbara Craton, but it's not really significant. The East Pilbara Craton, among many of the other Archean cratons, shows this very clear dome and keel structure, where there's the idea of you get in cross section here, granitic domes, you get shearing on the margins of that dome, and then you get steep fabrics in the keels that basically get pulled down into the crust in these locations. In the Pilbara itself, there's different models for how these dome and keel models form. One is what we've talked about, the convective overturn, where you get these generally older or syn greenstone belts. So these are komatiites, they're basalt flows, basically sedimentary and extrusive igneous deposits being formed. They form a density inversion with the lighter crust, and then you pull it down, and then that uplift basically initiates magmatism and causes it. An alternative model put forward by Zegers and others, but also by Kloppenberg, is that it's more like the dome areas were thickened crust and then they have gone into extensional collapse. And then the third model is that it's really basically a two bidirectional folding. So the dome and keels are really anticlines and synclines, or domes, structural domes and structural basins. And those are sort of the different models that have been talked about for the Pilbara. So here's Mount Edgar itself. And what you can see is it's not just a single phase of deformation. You're going to have to excuse my American pronunciation here because I don't do it quite the Australian way, but the Kalina supersuite and the Tambina supersuite, these are mostly migmatitic granitic bodies. These are the oldest, though. Most of the Mount Edgar Dome consists of this Emu Pool supersuite, which is sort of the volumetrically significant, but sort of forms a donut shape around, and that's the 3.3 billion-year-old granites. That, it turns out, is going to be important because we think that's when the dome formation is. And then there's this Cleland supersuite, which is younger, forms the middle of the suite. There is this split rock supergroup, which occurs in one place in sort of the western part of the Mount Edgar Dome. It's generally agreed that doesn't really affect it, and it's post-doming. So I won't talk about the split rock supersuite as we go forward. On the right-hand side of this diagram, and the key are just the different timings for the different keel or supracrustal rocks that are forming. I'll give you the names in the next slide, but the point being that they're coincident with the magmatism of the supersuites. They tend to kind of move in lockstep with them. So again, just going from oldest to youngest, looking at the dome-related granitic rocks. And I want to say almost all of this work was done by Nick Roberts, working with me as a PhD student and then a postdoc. And the important point is that these rocks have a significant age range. They have over 200 million years of an age range where you keep getting magmatism in one location. So this is very different from anything we're seeing in the Phanerozoic. And there's going to be other differences with other plutons that we study in the younger parts of Earth history. All right, so this is going to be a structural talk. So I'm going to just go through a few definitions so I don't lose people. We look at deformation fabrics in these rocks, and there's no markers, so we have to use the mineral alignments themselves. But the minerals can align, no matter what the shape of the minerals, they can align themselves into foliation only, so that there's no linear direction. They can align themselves into lineation only, so like a group of pencils where there's no fabric foliation. And then, but most of the time, they're going to be in this foliation plus lineation category where we can determine both. The other aspect we're going to use, the other technique we're going to use is the anisotropy of magnetic susceptibility, or the AMS. And this is using the magnetic properties of the rock to determine both the degree of anisotropy, PJ. So basically it's the deviation from a sphere or a circle. So if it's 1, that means it's basically equal. It's isotropic in all dimensions. You get higher numbers. You typically don't go above sort of 2s or 3s with granites in terms of anisotropy. So that tells you how deformed the rock is or how well the minerals are aligned. And then we get the shape parameter. So that's going to tell us the difference between lineation only, foliation only or this triaxial or plane strain ellipse. So those are the two things we need to keep track of. And this is just to say we do this everywhere. The data looks like this, where we're plotting the degree of anisotropy, this PJ on the x-axis, the degree, the shape going from pure lineation at 1, pure at -1, pure foliation at +1, and then these triaxial in the middle. And there's some spread in the data, but generally the AMS ellipsoid is quite good in terms of replicating the fabric. There's a lot of stations Nick took here. It's 153 with over 1,000 core specimens. And in general, the foliation and lineation from the AMS corroborate the field foliation and lineation. The AMS is particularly good for lineation because it's hard to see the linear features in the field. All right, so this is just foliation. For 3 different times, the Tambina, the old stuff, the Emu Pool, the middle stuff, and the Cleland, the younger stuff. The background for the stereo nets here distinguish the color that you see on the map. So the Tambina occurs mostly in the south and west portions. The Emu Pool, again, is a sort of donut in the middle, and then the Cleland is the stuff in that forms the whole of that donut. So the foliations, and also what's plotted is the poles defoliation rather than the foliation. We get a generally good pattern. It's easiest in the youngest rocks. Here we see it's clearly northwest, southeast striking. There's a clear orientation. The Emu Pool shows that same orientation, but it also shows some shallow dips, and those shallow dips are occurring in this area, where there seems to be a dome feature caused by the bowing up of intrusions from the Cleland suite. And then the Tambina suite shows that there are 2 lobes, basically, of different orientation. So it makes sense. The further back in time you are, the more complicated it is. Looking now at the lineations, and the plunge is shown in this plot at the bottom. And the fact that a lot of purples and blues are occurring in this area suggests there's steep lineations here, whereas in the western part, there's shallow lineations. Again, suggesting generally upward flow here, and I'll come back to this, but then sort of a lateral extrusion or a bulge just below the subsurface in this region. And again, that's reflected by the stereo with vertical in the Cleland, and then again, modified sort of 2 different lobes in the Tambina as you go back in time. This just focuses on solely the deviation from a sphere, and it suggests that they get the strongest AMS fabric here in the Cleland, and this is the place where we're getting the vertical lineations, but we also get strong AMS fabrics over this Corunna granodiorite, the dome, this minor dome. And this is just to show the densities, which is how many oblates we're getting versus how many prolates. All right, so one of the important things that comes out, if you look at just the Cleland, just the youngest stuff, we're getting mostly vertical lineations. And Nick did this very nice 3D diagram where he's showing both foliation trajectories by the sort of sheets, if you will, and then the lines give you the lineations. And so there's sort of a center shown on the map view for where you're getting these lineations. So I'm just to interpret that right now, that's the area that magma is coming up and then flowing out into these zones. And so that's sort of the root of the Mount Edgar, at least for the Cleland suite, for this youngest suite. Sort of show this more broadly. We just talked about the vertical lineations. You get radiating lineations that are pointing into the center, which really means it's moving out from the center. And then you have this weird arch shape. Against the margin in the old stuff, like the Tambina, you get these folds that are occurring, and that's associated with deformation, but that deformation is almost certainly caused by the later intrusions of the magma. So in other words, there's sort of an earlier phase that's getting plastered against the margins as these younger suites come in. What's really helpful with the AMS is to talk about the microstructures at the same time because the two form a very nice combination. And what we see in the domes is this combination of what these SMs, which are submagmatic, versus high HT, which is high temperature. So we see both um, high temperature deformation, when there's a little twist there, um, but happening in the magmatic or in the solid state. If you look mostly at the submagmatic, so these look like good granites, there's really interesting things. You see these little quartz stringers along some of the grain boundaries, and that suggests that there is melt present during the deformation of these zones. There's also quartz-filled feldspar cracks, so this is called submagmatic fracturing. So that means that there is melt present and there's enough stress on the rock that you're actually cracking open fractures, and yet you fill them by magma. So that's arguing that the magmatism and the deformation are happening at the same time. The quartz grains are not recrystallized, and the feldspars tend to be aligned as laths. So this is pretty hot deformation. There is, however, in different locations, solid state deformation. And this tends to be, so the M is moderate, the H is high, so moderate to high temperature, solid state deformation. And the quartz and the feldspar are recrystallized. Locally, you see basically subgrains forming on some of the quartz. And there's still evidence for submagmatic fractures. So if you look here, for instance, you can still see one of these quartz infillings in a plagioclase grain. So we're preserving the earlier texture, so it's not extremely deformed, but we're definitely deforming it at lower temperatures than the submagmatic fabrics. All right. Now that we know what those look like, here's the distribution of them. So again, if you start with the cleland, so the young stuff, it's deforming by high temperature deformation as well, so solid state deformation, but it also has evidence for melt in this area, and it's got both insignificant evidence and also minor evidence for melt. So, and the same is true of all the other units. They're all, you see high temperature deformation in all of these units, and you also see melt in all of these units. The one interesting thing is in the Emu pool in the north, we see it deformed as a magma with no overprint in this little prong, and it could be that that prong is unaffected by later deformation. Anyway, so that's the pattern. And so thinking about that with the idea of knowing what the lineations and foliations are suggest that you're getting melt present deformation everywhere. And the despite having different ages, they're sharing a common structure. So that argues that they're all being affected by an upwelling, the zone of upwelling, again, sort of in the middle of the Cleland suite, with lateral flow and then folding against the margins. All right, so a more recent paper, and this was led by Ross Salerno, again, very nice combination of microstructures with geochronology, is because we were as structural geologists wandering all around the Warrawoona Syncline area, we kept finding garnets. Ross was like, this is great. We can use some of those garnets. And we were able to distinguish microstructurally the garnets that pre-existed the deformation, the ones that were syn deformation, and then the garnets that were post deformation, and then able to date those different garnet phases. Okay, so we're going to do that. We're looking at this plot, we're looking at age on this graph, and then we're just looking at the different garnet populations over here. First, we have lutetium, hafnium as one dating system, and samarium neodymium, both for garnets. It looks like the lutetium hafnium are the more um, higher fidelity recorders of these plots. One important point is that the garnets are growing exactly when the different magmatic suites are coming in within error. So for instance, lutetium, hafnium dates for the garnets all overlap the Tambina group. So that's this one, and this one, or they overlap the Emu pool dates. So the deformation and the magmatism are happening at the same time by garnet geochronology, which basically supports our inference for what's going on in terms of the microstructures in the AMS. And the second thing is that we don't see them in the Cleland, associated with the Cleland suite, although the samarium neodymium garnet ages seem to be reset at this time. And so, but the Cleland suite is likely sort of the major push for the last of the doming events. So what's nice about this is it means that structural geologists know what they're talking about when they talk about pre versus syn versus post deformational garnet growth. All right, so how do you make all of that work? So the idea is that there's some kind of, at 3.3, we have the Emu pool magmatism, and that seems to be when we're getting the beginning of extension. The domes seem to be flowing up, and then the Cleland magmatism that's just 20 million years later, magmatism seems to sort of be rejuvenating the dome or continuing to uplift the dome. And that the Cleland is probably why the Cleland magmatism and deformation associated is what's causing the domes as we see them today. Although that process seems to start with the intrusion of the 3.3 billion year old Emu pool. Okay, so far, so good. Everything so far could support this convective overturn or sagduction model. So the Mount Edgar has a coherent dome-wide flow structure. The dome rocks of all ages are deformed at elevated temperatures. And then the hypothesis from all this is that the deep crust underwent significant weakening event. All right, that's the good. Now let's look at the problems. One of the problems is that the shearing basically is occurring all the way around the Mount Edgar Dome. But only on the south and west side. There's much less on the north and east side. Could this be an effect of the buttressing of the Corunna Downs? Perhaps, but the shearing is very prominent. And then the question is, what does that shearing look like? And this was the big surprise. When you look at the margins, and in general, the greenstones lie structurally above the granites. But every place we look at them, both in the greenstones and in the granites, no, we're going to back off that. The majority of the cases is that we find greenstone up shear sense, which means because of the overlying nature of the greenstones, it's mostly a reverse shear sense indicator. So that's odd. So that says the granites are moving down, but they're moving down during a deformation that we think the granites are intruding into. So that you would expect granites up, but we don't see that. Nick did a very nice job of looking at statistically which ones are up versus down, and it's basically a 75-25% of granite down shear sense. And so that's opposite what you'd expect from a simple convective overturn model. So the question is how to make that work. And in a paper that we worked on together, we speculate about how that could happen. One way is you might find zones of local contraction where you're pinching out the greenstones and pushing them up. Another possibility is that the Cleland suite is actually pushing out and pushing down locally on the stratigraphy. Or the third option is that we have some kind of crustal shortening, and that'd be particularly true if there was some strike slip in here during sort of oblique, some kind of oblique shortening. So those are different ways you could get it. Um, I'm also going to go back to this shot just to say Nick actually went around the Pluton and found out where you get the dome up sequences, and they're in the northwest, they're in the west, they're very prominent in the southwest, and they also occur on the southeast. So they're actually a good way around the margin that we see these dome down shear sense. All right. The next thing I want to talk about is this Warrawoona Syncline keel. So I've now twisted this so that north is oblique so that I could show this in more easily on a east-west oriented panel. A lot of units are in here. I'm going to pay attention to just two of them. One is the Duffer. The Duffer is going to be interesting because it's the most felsic of these units within the Warrawoona syncline. And then the apex basalt. And the apex basalt, because it hosts this zone of sinking, which I'll get to in just a moment. And so between Corunna Downs to the south, Mount Edgar to the north, it's quite thin in the middle, and it seems to fan out towards its western or really northwestern edge. Um, as we look at that, I'm going to give you two different tools that we're using. One is this thing called crystallographic vorticity axis. The short version of this is we can tell the direction of bulk rotation or bulk vorticity of a rock, independent of foliation, independent of lineation. So it doesn't matter what the foliation and lineation are. We can look at the misorientations of any individual crystal. We started with quartz, and quartz is used in this study. It's going to be used on the chert layers, but in fact, it works in any unit. And then you basically contour it, and then you find the axis of rotation. So in a sample system, so now in the sample reference system, looking at a stereo net, if it's a simple shear, we expect the axis of maximum rotation to be in the plane of foliation, so shown here, but orthogonal or 90 degrees from the lineation direction. The second thing we're going to do with the same EBSD data is look at the crystallographic preferred orientation, or CPO. I might slip and call it that. So crystallographic preferred orientation gives you three different things, or can give you up to three different things. It sort of depends on what pattern you get. It can give you the approximate temperature of deformation. It gives you something about the history. So did it happen by flattening, by constricting, by plane strain? And then if you get the right types of CPO, it can tell you about the shear sense. So I'm going to let the cat out of the bag right now. Everything we have is Prism A slip. So we're talking about relatively high deformations. It's thought to be basically 500 to 550. In some cases, you can get up to 650, um, depending on things like water content and strain rate and so forth. So, but we're going to be in this sort of 500 plus range, but we're not at the highest slip systems when we're looking at the Warrawoona Syncline. All right. And then the last thing we're going to tell you is the inverse pole figure, which you don't really need to worry about. All you're going to see is that everything plots here in Prism A, which means that's the active slip system. Then we're going to plot all the results in terms of constriction, flattening, plane strain, coaxial. But these patterns tell us that it's deformed by coaxiality, so there's no shear component versus these that are sheared. All right, this is the whole data set. So this is the publication figure, but I'm going to break this down and do it one by one. If we worry about just the places where we have cherts or quartz veins, so quartz only rocks, and we want to find what's the sense of shear. If you look in this part of the Warrawoona Syncline or over here, Prism A slip is happening. It looks mostly like simple shear from the CVA analysis, and we get a consistent asymmetry of the crystallographic preferred orientation. These are good plane strain indicators, and they all say dome down sense of shear. So that's good. There's a coherent pattern where the dome is down. It's consistent with the fabrics, the field fabrics we see. And they're consistent with the foliations and lineations that we measure as we go around. So basically, the lineations are mostly pointing in the same direction, but they're mostly down dip wherever they are. There is coaxial deformation, though. In this darker blue and found in this area, as well as in the southeastern margin, we have flattening. So that means you take a sphere, you turn it into a pancake. You're just smashing it together as if there are no boundary conditions. So the material can go any which way. In one area, we get it's still coaxial, but it's plane strain. And so this suggests that the movement is all up and down and it's laterally constrained. So that makes sense. So it's laterally constrained sort of in the middle. And then as you go towards the edge, it can sort of scooch out towards this fan shape area. So that makes sense. And it's very consistent with, once again, our field fabrics from the areas where the lineations are plotted as the dark lines, the poles, the foliation in the sort of lighter colored circles. So that everything holds together really well. So now we're going to get a little bit into the Collins et al. Model of what they did in a 1990s paper is they looked for the fabrics in this zone and they found an area of high constriction. And they said this might be a zone where things are getting pulled down into this zone of sinking associated with the sagduction or convective overturn. When we do the fabrics there, we get good constrictional fabrics. It's not an overprinting. You can't call on like orthogonal foliation development. The fabrics are truly constrictional, or at least the last ones are constrictional. Same prism A slip, so the same temperatures of deformation. We expect the CVAs to be wonky in this case. And we're getting good constrictional fabrics, which is basically small circles around the x-axis. So that seems to work. There's really strong along strike variations in the fabrics we're seeing. Okay. And yet within this zone, we see pretty consistent lineation trends. So the lineation isn't doing all that much different, but there really is this change from plane strain to flattening to constriction out this zone. All right, so there's a reasonable agreement of our fabrics with the Collins et al. Fabrics, but there really is something to this zone of constriction. So now what we're going to do is say, okay, we're going to go back in and do a gravity study. And I want to say the Collins et al. Model is a really good model. If I had their data, I would have hoped to have come up with something as good as they did. But this model, and I'll go into this later, predicts that the zone of sinking is because you're pulling down the dense mafic material there. And if that's true, it's a buoyancy-driven process, and it's got to have a gravity signal. So there should be a gravity high here. So that's what we're looking for. So I'm first going to go over this paper, which came out after we started our work, but it lays a great groundwork for the granite and greenstones of the Paleoarchean. And I think they did a really nice job. So they have basically airborne gravity, which is great. They have on the ground gravity at about a 2.5 kilometer grid spacing. And then they're going to have a seismic line along this that unfortunately only goes to the middle or the western, but still within the Mount Edgar Pluton. They didn't get across the Mount Edgar Pluton, but the results are really kind of important. All right, first that they noticed there is underneath the greenstone a gravity anomaly. But so now this is kind of complicated. This is just a map showing the Mount Edgar, Corunna Downs, and the other domes. And then they take the top portion off to show how deep these different keels are into the crust. And they go down some like up to about 10 kilometers, maybe 15 kilometers by the Mount Edgar. But they don't go through the whole crust. Um, and moreover, in the area we're interested in the Warrawoona Syncline, it seems pretty thin in that area. Because you can do a seismic velocities through this, they did an industry seismic approach, and you can use the trick of plotting densities from your seismic velocities. They were able to plot this diagram. And what they say here is you can't have whole mantle convection because the places, so these are these yellow places here, which are higher density, which means faster seismic travel, they don't go more than 10 kilometers down in the crust. And there seems to be an upper crustal effects going on and lower crust that has very little to do with the upper crust. So it seems like there's sort of a division of what's going on in the upper crust versus what's going on in the lower crust here. And so that's kind of interesting. All right. But we did something. So because this zone of sinking was the first place the convective overturn model had been proposed, we went and did detail over this area to determine that. And so we just studied just this one area to see, does this make sense? So this was an undergraduate project. Paul Kelso led this project with a bunch of students from Lake Superior State, University of Wisconsin, and University of Nevada, Reno. You know, standard, used good Lacoste-Romberg D meters, had elevation control of about 2 centimeters, which is overkill for the gravity corrections. Um, and then we put in spacing at about 0.5 kilometers, particularly across this zone of proposed zone of sinking. So this is admittedly overkill. Um, so it's over 500 gravity stations collected. We also use the Western Australia gravity grid outside. The zone of sinking is about there. So you can see that we've got pretty good coverage over that area. This is the Bugey anomaly map. So I'm going to take a drink while you look at that for a second. And I think even from the Bugey model, you can see you'd be hard pressed to figure out where the zone of sinking is here. So what we're going to do, but that's where it is. Um, but the gravity, the density, a high, a positive gravity anomaly exists to the west somewhere, and we're just on the gradient into that anomaly. So we did forward modeling along 3 cross sections, A, B, and C. B is the one that goes through the zone of sinking there. If you look at the first one, you can get the granites down, the greenstones down to about 3 kilometers. Gravity is not unique, so you can actually modify, you can match the observed, which is the black dots, to the calculated, which is the line, in a variety of different ways. This we thought was a reasonable way to try and do that. But there's no way to get the granites much lower than about 3 kilometers depth and still match that signal. As you go further west, the anomaly does get a little bit deeper. I should say we have really good surface control on the densities. We measured with a pyknometer. We have lots of density measurements for the different units, so we know pretty well what those units are. So we've modeled, for instance, the Duffer, which is unfortunately low density, but we can accommodate that easily. And so you can get signals that look like this, but again, not very deep. And as you go to the line further west, it gets the same depth or maybe slightly deeper. The greenstones seem to be more significant out there, which is consistent with the fanning of the map pattern. And again, they're no more than 5 kilometers deep. So now I'm going to show you all 3 forward models. I should say there's a 3-to-1 vertical exaggeration on all of these. There's no anomaly underneath the zone of sinking. And anywhere you go, the greenstones don't extend greater than 5 kilometers depth. Okay, so what does that mean? Well, there's no Bouguer anomaly associated with the zone of sinking. So there is no keel, at least here, which is where the convective overturn was first proposed. So either you can get rid of the keels completely cleanly in this case, or it just was never there in the first place. Those are your two choices. And the latter seems to like the simpler explanation. Okay, so if not there, if there's no keel here between Mount Edgar and Corunna Downs, where is it? Well, again, as you move west, we seem to have a high density. If it's anywhere, it's going to be at the intersection of Mount Edgar, Corunna Downs, and Shaw in this area, or there's another dome out here, and you have another deep keel there, or between Mount Edgar and two domes to the north. If these keels are anywhere, they're going to be under those areas. And what's interesting is all of three of those areas are covered by the Fortescue Formation, which is this overlying unit. And gravity, we can do the gravity inversion through there, but we won't be able to see the structures that are just above those areas. We'd have to just sort of use what's on the side. So that's sort of the things we're thinking about doing next, is trying to figure that out. There is this other problem, though. If that's true, I at least have no idea why there's constrictional strain patterns. It's got to be telling us something about the processes that are going on, but I really have no idea what it is. It seems like there's the Plato Fun Factory that's either extruding stuff up there or pushing stuff down there, and I have no idea which it is. And we're going to have to use sort of gradients of fabric if we want to sort that out. All right, so kind of finishing up here. From the AMS and fabric studies, microstructural studies in the Mount Edgar Dome, we seem to be saying that there must be crustal flow, and that crustal flow drove the doming of these rocks. So the idea is you have this long-term magmatic centers, and particularly the Emu pool and the younger Cleland come in at the same time, about 20 million years apart, and those are the two that seem to be in the sort of 3.32 to 3.23 broad range. It could be as short as 3.3 to 3.28 range. They seem to be what's driving it. They seem to be driving it in the absence of major extensional events. But we do have sort of particularly in the Cleland, a northwest southeast dominant foliation that suggests that there's some kind of unidirectional northeast southwest flow. So that's what we're getting from the domes. From the greenstone on the margins, we're getting this idea that there must be late stage movement, either caused by the Cleland suite or associated with some younger tectonics that we know. And from the gravity, we're getting indications that there might be these sort of zones of sinking, but we don't have the resolution at the moment to figure out where they are or why exactly they are where they are. But sort of these two black arrows point to two of the bigger domes, keels in the area, so the depth of the keels. And so if convective overturn occurred, it was likely happening at these triple junctions, but we don't understand the wall rock fabric, and particularly why we're getting local constriction. Okay, so the takeaways are, I went in to figure this out. We know a lot more than we did before, but we still don't know. There's parts of our study that agree with convective overturn models. There's parts that don't agree. And with that, I'll stop and take questions.
Great, thanks so much. Just a reminder, you guys can send in the chat and I'll read it out, or you can raise your hand with the react button or something like this.
Uh, okay, so Paul has a question. I can read that. So the quartz micro veins require a magma. It, we don't see quartz vein structures in these. They're magmatic. They are basically a single mineral that's coming in. They're very much like the submagmatic fracturing veins that are intruding. And so because we see that process in as a magmatic fracturing pattern, and we're just seeing it at grain boundaries. We're just inferring that it's the same mechanism from that. So it's an inference, certainly, but one that's generally consistent. It's a good question. It's hard to come up with other reasons. The other thing, Paul, is they tend to stay right on boundaries. They don't cut into the next grain. So they're really sneaking around the grain boundary. So it's kind of a wetting angle, what we think about more generally with melt infiltration.
Looks like Greg has the question. Go ahead.
Yeah, that was fascinating, Basil. It's a real puzzle. I was struck by the dome down business, which is not what I would have expected at all. And what I'm thinking is perhaps the whole thing is due to doming that resulted in the Fortescue Large Igneous Province event. Is that a possible explanation, which would make it kind of like the core complexes that we get in Idaho, among other places? Is that a reasonable idea? That it's all a bit later, this dome down business.
The dome down business could be later. Um, there's a couple things that would argue against that. The Fortescue is much later, right? It's
2.9 something, yeah.
2.9, exactly.
Yeah.
Uh, and so the garnets we're getting in these zones are suggesting that the garnet dating of the syntectonic garnets in the Warrawoona Syncline are older than the Fortescue.
Hmm.
That's not to say that the constrictional fabrics couldn't be older, but it says that anything along the dome should be about that same age, right? This sort of 3.28, 3.3 range. And so the dome down likely had to happen at that time.
All
So
right.
I think the geochronology, it's a great idea, but I think the geochronology rules that out.
And I know you're very familiar with core complexes. I think you gave us a lecture out here in Eugene once about it. Um, is that model completely out to lunch or unreasonable by your data?
Um, Again, everybody's got, I think the data that Kloppenberg got was exactly right. I mean, those data are good. It's just how you choose to interpret those data. And we have a lot more geochronology now. So it's harder to run a late stage core complex in that area.
Mm,
So it's not to say it doesn't happen, but it's much harder to make that model work
mm,
given the new data we have.
right.
I'm I'm kind of agnostic about, I mean, I'm just trying to figure this out. I'm kind of agnostic about why exactly it happened, right? All the models have some problems with them, but I would say there's less support now for the core complex model.
Thanks.
Yes, your own, I think you were next.
Thanks, Basil. That was a great talk, really interesting. A quick question: do you have any indication at which depth these processes took place? How far below the surface? Because I guess we see everything at the surface now, but I guess it wasn't at the surface at all when this all happened. Is any of your data giving any indication about this, or do we
That's
know
a
this from other
that's a
data?
great question. So what I have is temperature.
Mm,
And then the question is, what's the geothermal gradient in the Paleoarchean? I have no idea, right?
mm,
Um, so we have not worked enough on the geobarometry to say what that would be. I presume one could go back in with the garnet sillimanite rocks and sort of work that out. I've been really kind of hyper focused on the kinematics and the gravity at
mm.
this time. It's a great question. I don't know the answers to that, and it's certainly something worth doing.
Right. Okay. Thanks. Yeah.
I think next
Uh,
there's some in the chat here. On one side, you mentioned there is no indication of basalt beneath the dome. How was this determined? From Hua Huang?
Mentioned there's no indication of basalt beneath the dome. Well, there's the Hayward study um, of the regional scale, and if there was a large dome, if there was a large basalt province, we would certainly see it there. Our local gravity suggests that you might get small bits of basalt below, but it's not much. They're just kind of thin bits, no more than a couple 100 meters, maybe 500 meters wide in those cases. All right, and the second question is, what mechanism keeps the granite sufficiently hot and low viscosity to allow it to move and form the domes? Yeah, I would love to know the answer to that question. That is the key question here. And I've studied Phanerozoic and some Proterozoic granites. We don't see we don't see this kind of low viscosity over time, over sort of tens of millions of years, patterns going on, even with huge batholiths. The batholiths seem to freeze and then they act as rigid block for the next thing that comes in. So there's something keeping them hot. I have no idea. I mean, so you have radioactive elements that are a lot more active. It might be high geotherm. It's a great question. I just don't know the answer.
Paul, you can go ahead.
Yeah, the squeezing out of the synforms, topside up deformation style that you see is reminiscent of lobate cuspate deformation when you get a strain involving a rheological contrast. In other words, the granite and the greenstone. What's interesting is that the weaker material forms the cusps, which in this case would be the greenstones. You would expect that a greenstone would be stiffer than a granite unless grain size controlled rheology is ruling the condition that's pertinent at the time.
That's a great point, and I've thought a lot about that. So another thing I've been thinking about for why that might be the case if the greenstone is rheologically weaker is if you get amphiboles and you get them hot enough and small enough, you can actually push them into superplastic flow. And superplasticity has some, right? You can have very large ductile strains, relatively low stress, and no brittle failure, right? And so you might be able to do something like that, call on some mechanism like that. I have no evidence that the amphiboles are doing that. What I need is I need to find what's under those keels, and I need the amphibolites to sort of work it out. But there are mechanisms to make the greenstones much weaker. Is that at least a somewhat satisfactory answer?
Yeah, well, we certainly see that type of deformation on the scale that you observe in East Pilbara, which, in my understanding, the neodymium and other isotopes, probably hafnium and zircon, suggest there is no older basement.
Right. Yep. Thank you. All right. Could basaltic underplaying beneath the crust provide the heat needed to keep the granite mobile and drive dome formation? That's a great question. I had thought about that. I'm going back to share. And so I really like this study because I was hoping to do something similar to this, but sometimes you just don't get funded. If there was basalt underplating the Mount Edgar Dome, we would see it. And we just don't see it in these seismic diagrams. So it's a great idea. We think basalts are what's keeping some of the sort of the magmatic systems I'm studying now in like the Andes active, and they're basically keeping the crusts. I mean, it's a huge bit of crust, but for sure you would see these basalts, and you just don't see them. Um, and you can't underplate at the mantle, I don't think, and heat the dome. There's too much crustal difference. So we finally have at least an answer for the east part of the Mount Edgar Dome that I don't think that's a viable option.
Great. Thank you so much. Is there any other question? Oh, Don Davis. Here we go. Go ahead.
Yeah, great talk. Could a mid-crustal detachment explain the paradox?
How far do you want to move these things, Don?
Well,
Right?
far enough so you don't get any correlation between the upper crust and the lower crust.
It's possible to, right, it's hard to know how much to move it. That seems to me permissive, but really a tough explanation because you're going to have to move so much in and out unless you're going north and south, right? Along that seismic section, there's nothing that looks like basaltic underplating.
Mhm.
So what it seems really like what's going on in the upper crust is going to be different from what's going on in the lower crust. So in that sense, you're right. They might be somewhat decoupled. We certainly don't see the greenstones going down through that sort of mid-crustal layer. So that layering is inferred to be a sill. So I'm not quite sure what to do. I think one could entertain that, but I don't find that a high likelihood possibility. It's a good idea to think about, but
Mhm. Okay, thanks.
Yeah, across a detachment, you should see a contrast in rheological style, a ductile on the footwall and brittle or more brittle on the hanging wall. And so the juxtaposition in rheology would be the indicator of the transposition of depth.
okay. And again, I would have to really go into depth with the Hayward paper to say, do we see that or not? But it doesn't seem like we do. The seismic reflection only may not be enough to exclude the basaltic underplating. So dual velocity, yeah, that's true. Certainly more geophysics would help to understand that sort of setting for sure. All right, Alex, if there was a channel flow between the two domes within the greenstone, you might expect opposing sense of shear. Could this help to explain the dome down sense of shear? The issue is Corunna Downs is not particularly well exposed along its northern margin. And so it's an interesting idea to go to Corunna Downs and see if we have the opposite, but the rock record there is not so good. I mean, they made an airport out of it and they started flying airplanes in World War II. So this tells you the amount of outcrop we have there. It's a good idea, Alex. I'll think about that, about whether if it's opposite on the Corunna downside, then it might be something else. I also think there's something to do with that fanning out to the west. And I think the fabric gradients moving westward, which is what we haven't studied yet, might be the key to understanding the zone of sinking problem.
Okay, any last questions, everybody, before we thank Basil?
All right, well, thank you everybody for your questions and your attention.
Thank you. Really great talk.